Hello, this is Wenchen Fan from Databricks. So now you know what is CBO and how it works. Next, I will show you how you can apply CBO in your queries and improve the performance. And here, I will show the example with multi-way join, like we explained in the slides before. And this is run in Cleverest Cloud with runtime 3.0. So let's begin. So here we have three tables. The first table, customers, contains the ID and the name of a customer. And the second table is goods, contains the ID and the price of the goods. And the third table is orders, contains all the orders between the customer and the goods with their ID in the table. And I also prepared some random data to insert into these three tables. To save our time, I just do it ahead, and so we don't do it again here. Okay, let's write queries. So say that we want to find the rich people that buy $1 million goods in these three tables. So how to write this query? So it's easy. So you can just select the customer name from this customers, orders, goods, these three tables. And then we specify the where condition that we want the customer's ID equals to the customer ID in the orders table, and also the goods ID equals to the goods ID in the orders table. And finally, we have an extra condition that says we want only know the goods with price larger than $1 million. So it's a rich people. Okay, so let's run this query. And in the meanwhile, we can see the query plan of this SQL statement in the SQL UI. Oh, sorry, it takes. Yeah, also we can see that it will issue a first job first to do the table scan, and then it will issue following jobs. And let's see if the UI comes back. Okay, it's coming. SQL tab. And oh, the job is still issuing during the scheduler. So let's see if it's here. Okay, it's running. Oh, not this one. Okay, so here is the step to see the Spark UI. You click the Spark UI in the top left, and then you have this SQL tag. Okay, let's see this query. So remember that the query statement is join the customers table and orders table first with the condition, and then we join the goods table first next. So because the customer table and the orders table are both very large, so here Spark choose to run them with sort merge join, which means we will first add an exchange operator to shuffle each table, which means we will repartition the data across the cluster. So this means a lot of network I/O. And then we will do a sort to sort the data in each partition. And finally, we use run the sort merge join for each partition to finish the home join. And then here we have the third table, the goods table. So because we have no idea what's the output loss, a number of output loss of the filter operator, so Spark can only plan to use sort merge join for this second join. So there will be another exchange below the join result of the first join, and then do sort again, and then finally the sort merge join. So let's see how much time it takes. So it takes about 1.75 minutes. Okay, so let's see how to enable CBO to improve this query. So by default, CBO is disabled because it's the first release, and we will enable it by default in the future. It's simple. You can just set the conf spark.sql.cbo.enable equals to true to enable the CBO. Then, like we mentioned before, to really leverage the CBO, you have to collect the statistics for tables first. So here we use the command NAS table customers computer statistics for current ID. So here the customer name is not used in any predict or join condition. So we only need the statistics for ID. And then for goods and orders, we do the same thing to analyze the statistics. And the statistics is only needed to collect once for all queries. So, and also, the information will be stored in Metastorm. So here I also do it ahead, so we don't need to do it again. Okay, let's see if the CPU works to use a simple command to verify it. It's called the explain cost. So here we want to see the cost of a simple query. Select star from goods where price greater than $1 million. So let's see the optimized plan. So here we can see that the table relation has 100 million rows. And after the filter that price greater than $1 million, the CPU estimates the output rows about 100 rows. So you may ask, how good is the estimation? Actually, we can look at it in the Spark UI to see the actual result of the filter. So remember the first query, and we have the filter on the goods table. And in the Spark UI, that we show that the actual result number of output rows for the filter is 93 rows. So it's very close to our estimation. And CPU works well for this case because the data is evenly distributed. OK, let's run the same query again. OK, let's see the CQ. OK, let's see what is the query plan this time. So again, we do not change the join order. So at first, we still join the customers with orders. And because these two tables are both large, so we have to choose sortable join again. However, now we know that the goods table, after the filter, we will have about 100 rows. So it's small enough to be broadcasted. So here, Spark is smart enough to choose the broadcast join, which means we don't need to do a shuffle again for the intermediate result and the goods table. And also, we eliminated the sort for each partition. Let's see how fast it runs. So it's running the first job and running the next job. And meanwhile, you can see the Cleverest Cloud. So we have a workspace for all your notebooks. And also, you can create clusters with very easy setups. OK, it's closed. Also, there is a UI for you to check all your database and tables if you are interested. And also, this is the Databricks Community Edition, and it's free for all of you. So all of you can just sign up and use it. OK, so it's slightly better because in the Community Edition, there is only one worker for your cluster. So the shuffle cost is not so high. And so we only get a little improvement for this case. However, in Spark 2.2, we also introduced another optimizer called the join reorder optimizer, which can fully use the CPU information and better improve our queries. So to enable this, you can simply specify the spark.cq.cpu.joinReorder.enable equals to true. And then let's run this query again, the same query to find the rich people. OK, let's see what's the query plan this time. OK, now you can see that the join order is changed. So now we will join the orders table and the goods table first, because we know that the goods table is small and can be broadcasted. So the first join can also be a broadcast join. And then the intermediate result of this join is also small. So the second join is also a broadcast join. So for this query, there is no shuffle at all, and it's all broadcast. Let's see how, let's see how much time it's used. It's about 28 seconds. So compared to the first query, we actually have about like 4 or 5 times faster. So if you are interested, feel free to try it yourself in Cleverest Cloud. Thank you. Next.
Can you switch to the presentation mode?
Should we switch to computer?
No, it's OK. Do you have the slide. Yeah.
So let's change to the other speaker.
Let me. I think. Wenchen. I'm not that familiar. Can you go to the
demo?
After demo. Yeah. Okay.
Slide from the.
Yeah. Okay. Okay, I'm going to talk about the final section. The current status and the future work for the CBO project. First, I'm super excited to say that CBO will be available in Spark, Apache Spark 2.2. And as of today, I think we have Apache Spark 2.2 release candidate 4. So I think the official Apache Spark 2.2 will come out really, really soon. And you can turn on or turn off CBO features by this configuration parameter. Spark, SQL, CBO enabled, okay? And in the very first release, the default value of this configuration parameter is set to false, okay? Why? This is because, as of today, Spark is used in the production mode for many sites, and we do not want to change the system default behavior. Okay, and I think we do plan to enable this CBO by default in Spark 2.3. So I really encourage that everyone, you play with CBO with Spark 2.2 release. As for the current status, we have an umbrella Jira Spark 16026. And this umbrella Jira, you can see all the tasks. As of today, we have resolved 32 subtasks and more than 50 PRs. Okay, so actually, CBO project itself is a big project. We started the project at the end of last August, and until the middle of April, so it has spent about 8 months. And more than 10 Spark contributors were involved in the project. And we contributed, more than 7,000 lines of Scala code. I would say that CBO itself is a good framework to allow integration and future enhancement. For example, you can use statistic information to derive whether or not a join attribute is unique. And it can benefit, star schemas detection, and also so that it can help its integration into join reordering algorithm. Okay. Now I want to briefly talk about, how we achieve today. About 2 years ago, I myself and 3 other engineers, at that time we were with Huawei's research department. We prototyped CBO concept using Spark 1.2. And after we had a successful prototype, we shared the algorithm and technology with Zhenhua Wang. Zhenhua, he is one of the speakers. He implemented CBO in Huawei's big data product. And then last year, at last year's Spark Summit, we delivered a talk. I remember, right, on the same day, before the midnight, I received an email from Renaud Xin. He said that his email was brief. Can you contribute your work, your CBO work, to Apache Spark? Okay. Then this is what happened. So in the past 8 months, we work closely with the community, and Zhenhua Wang, he did the majority of the development work. I myself and Renaud Xin, Wenchen Fan, and Xiao Li will all help do some coding here and there. And for this project, we had more than 10 reviewers. And for each Jira and the PR, we had quite extensive discussion. I remember in one of my PR, I actually received more than 200 comments. So I would say that all the comments actually made the development time much longer, but it did improve the code quality. And I will summarize my experience working with a community. Yes, it is a great pleasure working with a community. Spark community is like a happy family, and also it's a very professional community. And I would encourage that you actively participate if you can. As for the future work, okay, today, so you have seen our query analysis. And I admit that today, this is the very first CBO release. It is not perfect at all. For example, like the current cost formula. The cost formula is, earlier I showed you it is a cardinality. We only factor in cardinality and also size, and also multiply by some weighting factor. This cost formula is very coarse, very primitive, very basic, okay? So with this cost formula, actually, we cannot tell the difference, the cost difference between short merge and the hash join, okay? So, yeah, and also, we kind of ignore the shuffle cost. And we do plan to improve the cost formula in the next release, okay? And then, other than the cost formula, in terms of a statistic collection framework, we also have some more work to do. For example, like a histogram. We know that histogram is very effective in dealing with data skew, okay? Also, there's a count mint sketch algorithm. It's a new algorithm that is effective in dealing with when you have a very large number of distinct value. Also, no matter how smart CBO is, there's always some place CBO cannot handle well. For example, like a UDF, user-defined function. So yes, there's a need for hint mechanism, okay? Also, today, when you have a very large table, people frequently use partition. So we want to collect statistics at partition level in addition to table level, okay? Also, some people say that, in big data, many tables are huge. And will you consider using sampling techniques? All of these are the possible features we may consider, okay? So today, we have shown you, the motivation for the CBO project, okay? As you know, Optimizer is the brain of a database engine, okay? So by introducing this core space, we hope, we have made some architecture improvement to Spark's Optimizer. And we also show you, our statistic framework, how we collect table level and the column level statistics, and how we estimate the cardinality for each operator. And also in terms of cost-based optimization, we show you how we do the build size selection and how we decide whether or not we want to broadcast, we want to use broadcast join. And also we show you, the way we perform n-way join reordering. Also, we have shared the TPC-DS benchmark. With all of this, I think our message will be, we encourage everyone, you play with CBO in the coming Apache Spark 2.2. So this is the end of our talk, and we welcome if you have any feedback or question.
All right, we have time for questions.
You want to mention your office hour, it disappeared because of...
Hey guys, thanks for your very informative talk. I'm coming from Amazon Redshift background and moving to more Spark work. One of the things that we do in Redshift is analyze tables daily, weekly, and preserve that so that any user of a Redshift cluster could have the benefit of the statistics computed, fresh statistics for their tables. Is there any way of preserving and loading the state of the analyze operation beyond a Spark session? So that is, is there some sort of weekly maintenance you can do with analyze so that any user of your tables can, not have to rerun it, basically?
Can you please repeat the question? We were not able to hear the first part of it. Sorry.
That's okay. What are the limits on the analyze part of doing cost-based optimization? Is it a state that can be preserved? Using the analogy of Amazon Redshift, you can run analyze daily or weekly and keep your tables up to date with statistics. But I didn't see any sort of method for preserving the state. And so I'm wondering if the result of analyze expires with the Spark session or if there's a way of persisting it for all of the users of your tables.
Got it. So the result of the analyze table command or the statistics that it analyzes is stored in the Hive metastore, meaning that it's actually persistent until the next time you refresh it. So for now, essentially, if your table actually updates, you would have to run the analyze command again. And in that case, we would construct all the statistics once again.
Hi, kind of along the same vein, I was wondering if it would be possible to allow data sources to provide their own statistics. Obviously, that would avoid, having to recalculate things if the underlying data source already knew things, such as like in Parquet files or other databases, things like that.
So the question is whether or not we will read some metadata from an outside data source. Yeah, I would say that this is a good feature we may consider in the future. Yeah, as of today, we don't do that.
Hi, so I'm curious, when you, how do you compute table size?
How do we do what?
How do you compute table size for your statistics?
It's basically a scan. Oh, the table size is, depending on whether if it's a Hadoop file system table, you can actually query the size. If I remember correctly, it's a fast statistic, which basically means that you do not need a scan to collect the table size.
Yeah.
Correct.
Yes.
Yeah.
So I'm a little confused. Is it just like the file size or?
So ultimately, it kind of ties to the question before, which is that there are some statistics which are referred to as a fast statistic, which means that you can just query some metadata in order to get that underlying size. Table size is one of these things, for if your data is let's say on S3 or maybe in the HDFS. There are other statistics, for example, the distinct values, the cardinality, and things like this, and that we sometimes use Spark to collect, which is let's say cardinality is in some ways just a count star on the underlying table. A distinct value is again some variant of a Spark query. So it depends on whether the statistic can be queried from some source, in which case it's super quick, or it has to have a scan on the underlying data.
Okay, and I'm sorry, one more question. So one thing I know or have seen about the TPC-DS framework is that it has a very specific kind of schema. For example, there are no unbounded string type columns. They're all varchars. And also there aren't any complex data types, no arrays or structs or maps. So I'm wondering if you have a suite of benchmarks for tables that don't look like TPC-DS and queries that don't look like those queries.
I would say that as of today, no, we have not done it yet. Yeah, no. We have basically, we have done benchmark tuning for about 2 months, and we focus on TPC-DS.
Yeah, although that's a great question. I would just said a meta comment. The reason that we show that, the 98 TPC-DS queries are excellent, by no means says that we have achieved our goal. TPC-DS is just one benchmark that databases use in order to demonstrate its effectiveness. But there are a lot of benchmarks. There are many cases in which your underlying data has massive skew, and these are all things that we'd be working on. And nested data is one such case.
Have you done any investigation into, in practice, the probability or risk of computing the statistics being more time than you save in the query optimization?
So computing statistics takes a longer time than query optimization. I would say that, because before I used to be afraid that in big data environment, some tables are huge. But then recently I have found out that when the data size grows, user also put more nodes, okay? So for us, when we run TPC-DS benchmark, not only 1 terabyte, but also 2 terabyte, I think the time to collect statistics actually is pretty fast. Usually, I think we collect statistics for all the tables and all the columns, and it took us, I think, about 14 minutes. If we only take those statistics for those columns that participate in the query, I think it will probably 5 to 7 minutes. It will be even shorter. Yeah.
Just to add to it, it also is a function of what statistics you collect, right? In theory, you can collect massively complicated statistics, but there is a reason that databases actually collect statistics that are very simple. And many of these statistics, especially the ones that we said about future work, like histograms, like sketches, there is also this thing about heavy hitters. Most of the databases, they basically collect statistics approximately, which means that they would actually, not collect all the heavy hitters, or they will not construct super high fidelity histograms. They would just keep some approximate statistics that can give them 80% estimation accuracy. And then there's also feature work around how you propagate those errors, how you bound them, and things like this, which are all very, very interesting problems.
I just have a question about the format of the statistics that we're collecting. Is this the same format that Hive uses to store statistics, or is this a custom format that you guys have built to store the statistics in the Hive Metastore?
I did not get it.
Is the question about the format in which we store this?
Yeah, for example, if you do analyze tables in Spark, would Hive be able to use those statistics? Or is it just something completely separate that is only for Spark?
So is the question in what format do we keep the statistics? Let's say basically if it's cardinality, it's stored obviously as a long and other things. Is that the question, or?
Yeah, and does that interoperate with Hive's? Because Hive also can store statistics. So is it the same format, or is it separate?
Yeah, so it does not, to the best of my knowledge, interoperate with Hive. Although maybe Wenchen can comment on it.
So we store the statistics as key values into Hive Metastore as table properties. So it's in a string format. And when we read the reason we use string because we want this to be readable for humans. So users can just get the table with the data and show it to see the statistics. And then we read it back and pass it to our internal class object and then use it.
And is there any way that Hive can use these? Or
no, Hive cannot use it.
All right, we're going to take one final question and we're going to go for a break.
My question is very simple because when I write a Spark job, so our data is 20 terabyte data per day. And when we process the data, we have a really bad data skewness. So when we use queries, so we always find some partition is running, take most of the time. Not a single stage. It's just some partition take times. But when I see our CBO, so is there any way you can use this hotkey? So currently what we are doing is we took those key out. We use our own way to optimize it. But we would like to take those ideas into this CBO so we don't have to implement ourselves. So do you guys have any idea, any plan to implement these features?
So you are talking about, there's some kind of a skew or distribution. Some partition takes much longer.
Yes. So those hotkey issues. So key value pair when you join the key. So what we are collecting data is the network data. So sometimes Google Map, it's very, very high traffic. So everyone using the phone will have this Google Map thing. And also maybe Google.com is very hot. Apple.com is very hot. So those keys, sometimes when we do analysis on the top of it, usually take way longer than what we expected than others.
I think for this issue, there are multiple ways you can solve it. One is at user level, you try to balance, use multiple, even some kind of created key, okay, try to balance it. And another thing is that when we found out that, for example, today, as of today, we prefer, if you need to perform join, okay, if some partition is not evenly distributed, actually there's one join algorithm, there's a broadcast join. Once you do broadcast join, then you kind of, how should I say, then you do not need to shuffle or something. Then you can, sometimes you can avoid this skew phenomenon.
But like I say, our data is 20 terabytes, so there's no way we can broadcast.
Yeah, no, okay.
To add that, so
broadcast a smaller table, large table.
For skew join, there is already some technicals that can solve this, but the issue is that you have to specify which column and which value is skew. So with CBO, I think it's possible that we can collect information that to know which column or which value is skew, and then we plan the skew join automatically. So this can be solved in the future.
All right, cool. Thank you everyone for attending, and let's give another round of applause to the presenters.